It's kind of a last-minute call from Carrie Howlett to come and introduce our speaker. So I didn't wear a UVU shirt, but I did want to show you that I have a UVU necktie to wear with my sweatshirt in case I really did. But we could have Brent come up. He's got the you know, we are really lucky to have Kim in our physics department. I'm more and more convinced of that we really got a good deal when he came to us in fall of 2012. He has his undergraduate degree from the University of Copenhagen, and then he has a master's degree from University of Alaska, and then his PhD from Utah State University. But what he does for research is really fascinating. He studies that part of the atmosphere that really isn't that well known, in the sense that we know all about the troposphere and everything that happens down here, and the stratosphere is easy to access. Above that, we have spacecraft going through the really high atmosphere, and so we know a little bit about that. But what comes in between? And that subject is called aeronomy. There's a lot of fascinating topics with that. So Kim is here to tell us a little about his research. And aside from his fantastic research, I'd just like to thank him for the incredible work that he's done with our students in getting them active and going with a lot of exciting physics things. So Kim, we'll turn the time over. Thank you.
Thanks. Do I speak loud enough for the system there? You guys can hear me. What about the camera?
We're okay.
You okay? All right. So my talk will be on the optical emissions in the upper atmosphere. Some will be known, some of them might be not so known. And then that was my first title, and then I thought about it after I submitted. I was like, that's a little boring. So I added an relation to space, weather, and climate. And after thinking about it for 30 minutes, I realized climate was a bad idea because everybody has an opinion about climate. And that would cause some controversy and put me in a bad spot. So I deleted the climate out of it. But I might give a little elbow to the climate as we go along. I was also told this was going to be for a broad audience, so if you have to see any juicy equations, it's not going to happen. I have one single equation on the slides. I have this one here. So the first slide is actually summarizing all of it. Space weather is the interaction between what happens on the sun and what we call the magnetosphere of the Earth. The magnetosphere is simply the envelope where the Earth's magnetic field is dominant. So the interaction between these solar phenomena, most like what we call a solar wind, which is a stream of charged particles, electrons, and protons traveling through the space between Earth and the sun. When they hit the sun, they interact with the magnetic fields, and we get space weather. And one of the consequences of space weather is the aurora. So actually, that was what I will say the next 45 minutes is one slide. So that's a very quick summary of it. The outline, put in there just for the sake of it, but I want to introduce space weather up front. So we have an idea what space weather really is. I said most people have an opinion about climate. That's because we have an idea what climate is. But a lot of people do not know exactly what space weather really is. So I want to just point out what space weather is. And we look at these few optical emissions. We're not going to go through all of them. There's plenty. But just mention a few of them. And finally, I will show what we're involved with here at UVU. Just to introduce these emissions first, on the outline before I just space weather first, and then optical emissions. We're going to start with just one slide of optical emissions. This here is a profile of the temperature in the atmosphere, going from the ground at this figure up to 250 kilometers. Now the atmosphere is divided into regions based on the temperature. And the temperature, again, is, for many years, it was thought of being a radioactive equilibrium between the incoming solar radiation and the outgoing long-wave radiation from the Earth. So the energy input versus the energy output, when they were in equilibrium, we would have a certain temperature. Then we started learning that ozone is absorbing UV light. Well, there was a bump right here. And then later we found out there's something called wave dynamics. We'll show some figures about it later. That could propagate up to about 100 kilometers. And what they do, they disturb this radiative equilibrium, and it forces it to be really cold. So they have a dip up here. Otherwise, it would just look something like that. So these optical emissions I put in here, I put weather and lightning well, that's an optical emission that is related to weather. We have a lot of other optical emissions related to weather. Anybody can name one that is not on here? Rainbow, the halos, they are all related to weather, but they're not in the upper atmosphere. Then there's something called sprites. This is less known to most people. How many in here know what a sprites are? Yeah. All right. So there's one. Phil knows it. We have translucent clouds. Unless you live in northern latitudes, you may not know what translucent clouds are. Although you're starting to be able to see them down here. That's what's related to the climate. Then there's something called airglow. It's very, very faint. Unless you study it, you probably don't know what it is. We have meteors, or shooting stars, and then the aurora. And I'm quite sure everybody have heard about the aurora. But how many have actually seen the aurora? A few? Where have you seen it?
Minnesota.
Minnesota? How about you, Phil?
Finland.
Finland. Okay, so one is what we consider high latitude, where the aurora is more common, and the other one was Minnesota, which is what we call mid latitude, where it's more rare. So we're going to look at a couple of these, the aurora, airglow, and just briefly the sprites. So before we define space weather, I just want to introduce what space physics is. There's three components to it. It's what we call heliospheric physics, and it's the study of the sun and its environment. And by the environment, we mean the area or the regions where solar physics is dominant. That's inside what we call the heliosphere. So right here we have the sun in the center of the solar system, and around here we have what we call a shock. Now, the sun is emitting these charged particles. When you have charged particles in a gas, we call it a plasma. It's like a fourth state. We don't talk about Earth with a fine plasma, but we have a solid, we have a liquid, we have a gas, and then we actually have a plasma. This plasma can interact with the intergalactic plasma, although it's very thin, but where the boundaries are, you got these shocks. Inside the shock is what we call the heliosphere. And that's the area or the region where solar physics is the dominant mechanism for whatever is going on. Then we have a branch called magnetospheric physics. That is when the solar wind from the sun is interacting with the magnetic fields of planetary objects, like the Earth, for example. This interaction between the solar wind and the magnetic field of the planet is what we call magnetospheric physics. And then finally we have aeronomy, which is what I specialize in. And aeronomy is a little bit different in that sense. It's a relatively narrow region in the upper atmosphere. But it's very interesting because we have to take into account what happens outside. So that is in the magnetosphere. The dynamics in there interacts with the upper atmosphere, for example, in forms of aurora. It sets up electric currents. It's causing disturbances on the ground from space weather. It's causing disturbances in the satellite environment, and so forth. But besides that, we also learned within the last 10-15 years that whatever goes on below, from thunderstorms, convective regions in the equator, earthquakes for that matter, is producing disturbances that's also be felt in this region. And furthermore, these disturbances can actually propagate into the near space environment. So, space weather and climate, we have to have a distinction between climate and weather. And again, everybody have an opinion about weather and climate, but what about space weather and climate? What kind of time frame are you looking at when you talk about climate, for example? Is that something taking place over a year, weeks, many years? Anybody?
Many years?
Many years, exactly. But how many years?
22.
22 years, okay. Why 22 years?
Well, okay, 11.
So regular climate,
cycle.
if you ask a climate scientist, if you read the newspaper, climate, well, that's something that can happen this winter, because if the winter is warm, there's certainly no global cooling. However, if you ask a climate scientist, they will say, well, anything below 30 years, you can't relate that to climate. You have to look at something that's larger than 30 years. Similar with space weather and space climate, we have to distinguish what happens on an everyday basis versus something that's long term. Now the sun has some cycles, which is shown a little bit. Some of them are related to space weather on a daily basis, some of them are related to what we call space climate. So in order to talk about Earth's climate, this is my climate bullet. There's a lot of climate models out there. But there's also some controversy with the climate. The input goes in, and that's the known input we have. But what about the unknowns? There are some groups that have talked about that you have cosmic rays coming from the intergalactic background. Well, that's great, but cosmic rays penetrate into the Earth's atmosphere. Some research show that there's actually a correlation between cosmic rays and cloud formation. We all know that clouds are important for climate because they reflect light, but they also trap in heat. But how does that correspond to space weather? Well, the solar wind, how it interacts with the Earth's magnetic sphere, this solar wind is actually shielding us from cosmic rays. So when the solar wind is changing, the influx of cosmic rays also changes. That's one example of where those parameters may be likely to impact climate. However, they're not in the climate models. Then we have space weather. You probably heard about space. That's why you heard about space weather. How it can impact technology. It can take out radio communication, GPS satellites, and so forth. And then we suddenly impact it. Try, for example, for just one day, take all technology that is depending on radio waves or GPS signals. Take them away, just for one day, and try to see how the life will be. It's very interesting if you actually just try it. Do it on a Saturday or Sunday, by the way. So here's a graph, figure I should say, just illustrating some of the things that are impacted. So we have the sun emitting these particles, radiation and so forth. It reaches the Earth and interacts with our environment. We have satellites that are impacted. We have currents that's being set up. The solar wind can at times embed a magnetic field. It is actually the Earth's magnetic field. It's changed the magnetic field. You go back to Earth's discovery, when you take a wire, you send a current through it, you generate a magnetic field. Well, guess what? Upper atmosphere, about 100, 150, 200 kilometers up, we have those currents flowing on a daily basis. If there's no disturbances, they're constant, so we have a constant magnetic field generated from them. However, every single time we have a disturbance, it will fluctuate. If you have what we call a magnetic storm, it can be very violent fluctuation compared to these daily normal fluctuations. We have GPS signals that can be modified, even fail. Of course, our aircraft relies on them. If you're a farmer, you actually seed your big farms now using GPS technology. If you have a captain of big ships, big tankers, container ships and so forth, they all navigate through the GPS systems. The pipelines, so they have talked about, if you saw the talk before, about pipelines. Talk about how those pipelines react to earthquakes and so forth, how in Alaska have built them so they can actually withstand earthquakes. If you ever go to Alaska and look at the pipelines, well, there's a bunch of other little devices on them. What happens is, you have these long pipelines, well guess what, that's just one long conductor. If you take a conductor and you have a time-varying magnetic field, you will induce currents in the conductor. Well, the engineers, when they built the pipeline, forgot that little fact. So the pipeline was supposed to withstand time for so long until it will, doesn't rust, what does it do? Corrode, that's right. Corrosion, withstand corrosion. After a few years, it started to corrode. And it was like, why is that? Well, if you have currents, you're corroding the materials faster. So what they ended up doing was they put in different places on the pipeline, there are discharge mechanisms to discharge the current that's being set up in those areas. We still have them in the ground. The ground is a conductor. If you take the class from Emmerman, anybody taking a class of Emmerman? No. All right. So if you end up doing that, you may actually end up going out with some small measurement devices to measure the resistivity or conductivity of the Earth. You send a signal through, and you can measure the voltage or potential difference across them. Space weather can do that as well. The problem is when you're doing geophysical exploration, you're using similar techniques. So if you're doing those observations and you don't take into account what the ionosphere is doing at the same time, your readings will not be accurate. So you might think, oh, I just found a nice oil well here. No, what really was happening was you just had a roar above your head. So in more detail, the space systems that can be influenced is anomalies. If you have an instrument in space that's supposed to continuously measure temperature, that can be impacted by the space weather phenomena. You can have 2 or 3 days, for example, where you might not get any data. Depending on what you're studying, 2 or 3 days of no data might be very essential. It's like a government lockout. Orbital changes, well, that's a very important one. If the orbit of the satellite is supposed to stay in a certain orbit, that orbit can stay there for maybe 5 years. If you start degrading the orbit, it takes 5 months to fall down in the ocean. So these orbit degradation are very essential. So you want to know exactly what is happening, when it's going to happen. That's where the nowcast and forecast of space weather comes in. If you're doing spacewalks, or just in principle an astronaut, you should be concerned about radiation exposure. In fact, if you're a stewardess of an airplane or a pilot, you should be worried about radiation exposure as well. But most people don't pay attention to that. The ground systems, well, we have the GPS, long-range radio communications. Most people are not too worried about that. We don't communicate long range in that sense. However, the Department of Defense does that. They use low-frequency waves to communicate, for example, with submarines. During magnetic storms, they lose communication with the submarines. Again, radiation exposure, and we have the ground-induced currents, which is influence the geophysical exploration. So, if you look at the sun itself, I'm going to go back to the roots of all evil here. We know it emits light, electromagnetic waves, travel at the speed of light. They also emit particles, the electrons and protons. This is what makes up the solar wind. There's a constant stream of particles being emitted from the sun. And in a plasma, you can have what we call a frozen magnetic field. So this solar wind can transport a magnetic field. It's actually not transporting a magnetic field. What it is, for those of you who are physicists, is transferring magnetic flux. The active cycles of the sun, some of them are known, many people. Hopefully you're familiar with this 27 days. That's how many days it takes for the sun to actually make one revolution. There's 100 days development period for active regions. Active regions are these solar spots, or sunspots. So the dark regions of the sun, which have very, very strong magnetic fields. That's where solar flares comes from. Coronal mass ejections, which ejections are very, very high energetic particles. We have an 11-year cycle. That's for the solar the sunspot. They increase in number, decrease in number in an 11-year cycle. We have a 22-year cycle, which is where we have a reversal of the magnetic polarity of the sun. Now all those, actually a couple more, an 88-year cycle as well, which can be seen as an envelope of the 11-year cycle. And then there's a 205-year cycle as well. So all those cycles are, if you go back to climate histories of the Earth, you can find these cycles in there. The interesting thing is this is 205 years cycle. That was what caused what people believe caused the Maunder minimum. So a very, very cold period of time on Earth, the small ice age. An interesting thing is we actually overdue now on this one. So some of you might have heard that it hasn't warmed in the last 10 years. Anybody heard about that? Read in the news? So therefore global warming is a hoax. But I would say, well, maybe it's this one that started. We're actually hitting it like a small ice age now. But there's a lot of controversy on that. So if you go to interplanetary space, it's all dominated by the solar wind. So that is high stream of flow of particles, electrons and protons. The disturbances from these, or we have a disturbance on the sun, is a discontinuity in the solar wind. So for example, you might have a solar wind traveling at 300 meters a second, and then suddenly you get a flare or some other disturbance on the sun that's spewing out something that travels twice as fast. Well, when you have something that is going at a certain speed, you have something that comes at a different speed, as it's passing it, you get these shock waves. It's these shock waves, when they interact with the Earth's cavity, this magnetic field, that's creating our space weather. So the Earth's magnetic field, in principle, it's a dipole. That's at least what we like to think it is. But we see it from the outside, it doesn't look like a dipole at all. That's because it's interaction with the solar wind. I have a slide later to explain that a little bit more. But the cavity of the magnetic field is what we call the magnetosphere. And it's the dynamics inside the magnetosphere that is propagating down towards the surface of the Earth, or what we call the near space environment, and that's where we get our space weather from. So I listed 3 types of weather storms, space weather storms. We have what we call the radio blackouts. That's X-rays coming from the sun. So these are electromagnetic waves traveling at the speed of light, which means they get here in roughly 8 minutes. So there's very little warning when these system happens. The impacts are any radio communications that might be possible. We have what we call radiation storms. These are energetic particles. They're very energetic particles coming from coronal mass ejections. And they typically arrive to Earth within a few hours, up to 24 hours. So they're traveling not at the speed of light, but they're still traveling at like 100,000 meters a second or more. These particles are guided by the magnetic field of the Earth, so the strongest impact of those storms are felt at higher latitudes. Now, you can say, well, that's not so bad. I mean, not a lot of people live down in Antarctica. Few people live in Alaska, northern Canada. But the problem is a lot of our satellites are orbiting the pole. So when you do that, you're exposed to it. The impact, aside from the radio communication, is also ionization radiation, which cause satellite failure. You set up small current systems on the electrical devices or the electrical payloads in satellites. And there are numerous experiments that have been shut down because the satellite encountered one of those radiation storms. And finally, we have what we call the geomagnetic storms. Geomagnetic storms are caused by interaction with the solar wind and the magnetosphere, but it's because the solar wind can carry this magnetic flux with it. And that is what is interacting with the magnetosphere and causing particles to get down to the lower altitudes. The arrival time is typically 1 to 4 days. So that's why we have a nice warning. When we know there's a solar storm, you might see in the newspaper it's a big solar flare. People in Minnesota can expect to see aurora in 3 days. It's a nice warning we can have. The impacts of that is the same as before, but we also have electrical power grids because these geomagnetic storms, what makes the difference from the other ones is they set up large-scale currents in the upper atmosphere. Large-scale currents produce magnetic field disturbances at the surface of the Earth. That's when you get the electric power grids outages. We also increase the satellite drag simply because of the amount of particles being ejected into the lower atmosphere where the satellites are. And finally, the aurora. So the aurora is not per se reducing space weather, but it's an effect of space weather. So I'll spend the next couple of slides talking about the aurora. This is just a nice image taken from, I believe this was northern Canada, of what we call a auroral arc, auroral light. So to try to understand why the aurora is formed. So I said earlier, the Earth's magnetic field is approximately a dipole. So here's an artist rendering. I usually refrain from using artist rendering as a scientist, but in this case I did. So this is, if you take the dipole, it's a three-dimensional. If you ever take a dipole, a magnetic dipole, put a piece of paper out of it, take silver fillings, and drizzle. Have you all tried that? No? Alright, you need to come to our stockroom because we actually have iron fillings in stockroom. You can do that. You get a two-dimensional cross-section of how the magnetic field look like, and a dipole of these kind of rings going from north to south on the outside of the magnet. If you look at it in 3 dimensions, you get this kind of donut shape. There's a hole in near the poles, and what the red regions are what we call the radiation belts. So in the Earth's magnetosphere, this would in principle, if there's no solar wind, this would be the Earth's magnetosphere. And there's trapped particles in it called the Van Allen radiation belts. Now these radiation belts typically goes down to maybe 1,000 kilometers above the surface of the Earth. So they're not of any particular danger to us. And even 1,000 kilometers, astronauts can say, nah, we don't care. However, if you've gone to the moon, say the moon is sitting out here somewhere, you have to travel through them. Then you have to think twice. But you may notice, near the poles, these radiation belts are roughly about 1,000 kilometers above the Earth. If there was any way we could push this envelope together, you might imagine these particles would come down closer. And that's exactly what happens when you interact with the magnetosphere. That's what we have here. This is a disturbed view of a more realistic view of the Earth's magnetosphere, the magnetic field. So we have the solar wind. The solar wind has embedded a magnetic field. Magnetic field lines do not cross. If you ever try that in a physics problem, try to cross magnetic field lines, it won't work. So what happens is each magnetic field, the Earth's magnetic field and the solar wind, you can look at 2 different plasmas, will exert pressure on each other. It's similar if you're running against a wall. Well, it's going to be stopped. If you have wind flowing into a mountain, it's going to be stopped. Well, what does the wind do instead? If you have wind coming into a mountain, what happens with the wind? Goes up. Goes up or flows around it, right? The solar wind does the same thing. It flows around this obstacle, just like water meeting a rock in the river. However, these are plasmas. They act like fluids. So when you get on the flanks of the magnetosphere, imagine you have some jello sitting there. You put some very, very sticky whipped cream on top of it, you try to spread it out. You see the jello will kind of move with the whipped cream. At a certain point, the jello will say, nah, and swing back. Yeah? Just because you have this viscosity between the 2 liquids. Same thing with plasmas. So what happens is that as the solar wind moves around the magnetosphere, it drags the magnetosphere with it, or the magnetospheric plasma with it. And these magnetic field lines being stretched out in what we call the tail, away from the sun. Now what happens next is then the 2 causes of the aurora. We have particles sitting up here. This is a plasma. It's full of electrons and protons. It's sitting on magnetic field lines. So in physics 2020 and 2220, you will learn that if you have charged particles and magnetic field lines, these charged particles are confined to move around the magnetic field lines. So what happens, let's see if we can get this to work. Oh, that's not sound. There's nice music to it. So just play it again. ends. What you see is the magnetosphere. The solar wind is coming from the left. First you have a constant flow, but then you have increased pressure, so you have a solar disturbance. You can see it's compressing it on the front, and on the back, it's dragging it out. When that increased pressure then decreases again, it goes back to original configuration. When it goes back to the original configuration, the particles that's been first stretched, maybe you take a rubber band, you put a couple of pebbles on the rubber band if you could, and you stretch it out. And the pebbles are free to move, there's a little bit of friction, you move with the rubber band, you stretch it. You let go. What do you imagine happens to these particles? It's like a slingshot, right? And where they've been sent to? Well, along the field line, down towards the polar regions. When these particles hit the polar regions, they interact with the molecules and atoms in the Earth's upper atmosphere. They excite these molecules and atoms. When they decay back to the ground state, they emit light, and that's the aurora. So that's what we call a magnetic storm. The magnetic substorm is slightly different. In this case, the magnetic field from the solar wind and the Earth is actually in opposite directions, which means at a certain point, you get a magnetic field that's equal to 0. And that's the time when the magnetic fields can merge, and they're being dragged along. What you get is you get an inflow of plasma of particles into this region. This is also the one that's more prominent in stretching the magnetosphere out. So you get these particles in here, then they reconnect, and you get the slingshot again. This is a magnetic substorm. This is when if you happen to see a aurora that's very dynamic. A dynamic aurora, you can stand and look at a aurora arc in one horizon, and within 30 seconds, it's spanning the entire length from horizon to horizon. Like 1,000 miles or more in 30 seconds. That's a substorm. So there's two different mechanisms for creating the aurora. Although if you're watching the aurora, it might be difficult to tell which one created what. So as these electrons and protons interact with the other atmospheric molecules, if you look at the composition of the atmosphere, you will find it's mostly nitrogen molecules and oxygen atoms. Now the energetic content of the electrons coming from the solar wind or from the magnetosphere is such that it can create or excite the neutral molecule, but also the ionized molecule. You get these emissions. So this is mostly red and mostly blue. Now we won't see this a lot. This is less than 430 nanometers. This is right about the limit where we can see. This means to see a blue aurora is really, really rare. This red part is also rare because it's actually past 650 nanometers. Again, that's a region where we have very, very difficult seeing. However, we have one atomic oxygen line sitting right in the middle where we're most sensitive, the green line. That's why the auroras always appear to be green. There's another atomic emission, this is right around 630 nanometers, which is one we can see as well. But which one of those two contains more energy, green or red? Green. So the green is coming from the more energetic particles. The more energetic particles propagate further into the atmosphere. This one occurs around 110 kilometers. This one, on the other hand, is right around 250 to 300 kilometers. So it's up much higher. So if you stand from a distance, you see aurora, you will see green and then red, simply because the red is up much higher. So here's an example that you see from a distance. Got a lower green border, you have some red up here, there's some purple in here, but that's just the interaction of different colors that they combine. Here's another one, very green. Now you see some blue here. Now you will not see this when you realize. You might see this is very diffuse. That's because it's a longer integration time on the camera. If you just set a camera out there and then integrate for a minute or two, you're definitely likely to see some blue light. Now there is one thing that's very different in these two images. Anybody can spot that? aside from the colors, of course. Sitting right here. Yeah, this is sunrise. And that's the key to the blue aurora. The blue aurora is a resonance scattering mechanism. If you want to see blue aurora, you have to have sunlight hitting the molecules. So you have to look at this in twilight. That's why most people don't see the blue aurora, because people go out at 10 o'clock at night, oh, there's a nice green aurora. They go out at midnight, there's a nice green aurora. The blue aurora comes at twilight. So if you're looking for the blue aurora, you have to go right around sunrise. So jump straight to sprites and airglow now. The sprites was first documented in 1989. There have been a few reports about it earlier. Some pilots have seen these flashes of light going up in the sky. They reported them, and the manager said, "You've got to be crazy." So they were taking off flying for a couple of months until they would be evaluated whether they were mentally ill or not, and then they were reinstated. When they saw them again, it's like, I didn't see it. Didn't see nothing. So first in 1989 was actually documented by a team of scientists from the University of Minnesota, and since then it's been taken off. Short-lived, few milliseconds. You can see them from the ground, but in a few milliseconds, you really have to look for them, otherwise you won't see it. The true propagation was actually first real when you started using 10,000 frames per second cameras. So for 15 years, up to about 2000, everybody in the community thought that these sprites were actually coming from below, propagating up, and then they developed these 10,000 frames images, and it showed that it was actually balls of ionization that was traveling down, and then another set of balls were then released traveling up. So I have a video showing that.
This is not just a letter.
I didn't mean the
They're not usually this thin, this light.
Alright. This is Japanese team. So it's something very fast, but it's very fascinating. And there's a lot of things going on there. If you're into nuclear physics, it's a great place to do it as well. There's a satellite dedicated to look at something called terrestrial gamma ray flashes. And it's looking out in space because they thought they were coming from space. And they only saw a few. Then they have instruments that then point towards the Earth, and they saw plenty of them. It comes out from these thunderstorms creating these sprites of these terrestrial gamma ray flashes. Now the impact on climate and space weather, we still really don't have a clue about that. It's still a very, very new phenomenon. So there's a lot of work to be done here still. But it is a release of electromagnetic energy into the atmosphere, so somehow it is disturbing the energy budget. We just don't know the impact of it. So here's another video. This is from Dave Semin at University of Alaska Fairbanks, studying sprites. I just want to point out, this is a clear sky, except that what you have down here are clouds. And you start seeing these flashes going up here. These are the sprites. You see the clouds of ground lightning. You see the small flash coming up here. But notice this, all this white stuff here, it's not clouds. That's air glow. It's a very, very dense glow of emission. We cannot see with our naked eye. But obviously this camera showed it quite well. Actually, just play it again. You may notice that it seems like a ring propagating outward, as if you took a rock and dropped it in water. These ripples coming out of it. These are what we call gravity waves, or atmospheric gravity waves. They're not gravity waves in the sense that astronomers think about it, but atmospheric gravity waves, or buoyancy waves. Just propagating up from the thunderstorm. The thunderstorm is the source of these waves. It's just one of many sources. So what is the air glow? This is a really nice picture thing. I don't know where it's taken from. But you see some green glow here. This is the same green emission you see in aurora. I believe this is taken, I think it's from Mexico. I'm not sure. Of course, in Mexico, it's not polar latitudes, so you don't get the aurora there. But instead, you have this green glow, and that's the air glow. You see some structure in there, which is these gravity waves I showed in the video earlier. So there's three forms of air glow we distinguish between. There's day glow, that is formed by simply the ionization, excitation from direct sunlight hitting the molecules in the atmosphere. Like the oxygen, for example, before. It's the same oxygen that was excited by the energetic particle from the magnetosphere. We have twilight glow. That's when the observer is standing in darkness and the sunlight is hitting from below. It's the best time to see air glow if you ever have a chance of seeing it. However, twilight is a very, very short period, so it's not good for doing extensive studies. Then we have the night glow. Night glow is not formed by direct solar excitation. Instead, after the sun sets, you have all this soup of excited or ionized gases in your atmosphere. They recombine from chemical reactions. These chemical reactions are emitting light. This is the night glow. I really want a camera that can take pictures like this down from Carousel Reef. It's a beautiful scenario. This is taken from space. You might recognize this is a delta, Cairo. And you have a thin, green-looking band around the Earth. It's there, all around the Earth. A thin layer, roughly 10 kilometers thick, of this green light. There's also some yellow light in the sodium, so that's why it looks a little bit green, yellowish. And at first you might think it's a UFO. So in fact it was until I realized it's just a reflection in the window of the International Space Station. So the spectrum, I showed before the spectrum of the aurora. We had the green line, which is also the aurora. And this red line, which occurs much higher up in the atmosphere. And then we have something in the near infrared. This is not in the aurora. There's a little bit in there, but not much of it. And what you measure with a CCD, for example, is the integrated emission, which means if you take the area under the curve, that's the amount of the energy content. Well, where do you have most energy content? Right here, right? Which means if you could get a near-infrared camera, you have a great opportunity of studying the air glow. Otherwise, the green line is a good candidate as well. This is the yellow line, sodium doublet. It's not excited by energetic particles from the magnetosphere. So if you are at high latitudes, you might want to pick this one because the aurora is not going to influence it that much. So these are the rough altitudes. These are examples of air glows. These are colors are false. It's just black and white, monochromatic images. All skies is 180 degrees from horizon to horizon. And you see those band structures. Those are these waves coming, for example, from the thunderstorms. So here's a movie. This is from Mike Taylor of Utah State. Maybe not. Should have it in here somewhere. All right. So you can't see that one. All right. But if it work, you will see this was a clear sky. You see a very, very bright soup of emission. And you see these waves propagating. This would be a 4-hour. And you have waves coming from any directions. It's all night long. The question is, where do these waves come from? How do they affect the energy budget? And it turns out these waves are driving a major circulation of the atmosphere from pole to pole. They were causing this very, very cold dip. Remember one of the first slides showed it was very cold in the highest region of the lower atmosphere, the mesosphere, the mesopause. It's because of these waves. In the last 10 years, we also found out these waves can actually propagate even higher. And they have effects all the way up to 1,000 kilometers in altitude. Now that become exciting because a lot of scientific satellites is orbiting right around 600 kilometers in altitude. This here is another example, it's another image. Anybody can tell me what these blue dots are? Hawaii, that's right. It's a joke in Hawaii. Yeah. All right. What about the red line?
The fault.
It's close. It's this tsunami that hit Hawaii from the 2011 Tohoku earthquake. These waves was following that line. The tsunami was generating waves in the atmosphere that propagated up to, this is the red line. So this is 300 kilometers up in the atmosphere. The tsunami generated waves that propagated up there. If we had cameras or we had a satellite looking down the Pacific, we would see this wave traveling from Japan and all the way through to Hawaii. So that's another source of them. The effect of space weather is very interesting. When they propagate up through the atmosphere to the thermosphere into like 200-300 kilometers, so this is another emission of 630, so 300 kilometers altitude. That's a plasma. Now, a plasma in principle is not really sent to these waves. However, the waves perturb the neutron molecules, which then collide with the plasma, and what we get are these instabilities. And these are, again, this is roughly 1,000 kilometers across. So these are large scale. If we could see these in altitude, we can do that using radars that are looking at slant range at a certain altitude, and then you scan up through the atmosphere. These goes up to about 600, 700, 800 kilometers in altitude. So you have these depletions, these disturbances, and our satellites are flying through them. Sometimes we see they're like, what happened to the satellite? We lost communication for half an hour. There was no solar storm. So what caused it? Well, maybe these, what we call spread F, these depletions of plasma. It's complete environment. You have shock waves following them as well. So the last 5 minutes, I'll just spend on the research we're actually doing here, called space research. But combine atmospheric and space research. This is an instrument we have up in Alaska that's actually measuring these waves. Now, measuring up in Alaska in the polar latitude is a completely different story than putting an instrument up at Bear Lake. Because at Bear Lake, you do not have the aurora. The aurora is much, much brighter than the air glow, so we have to tweak it a little bit. So you won't see as pretty images. However, if you do a simple analysis just by subtracting images, they act as a bandpass filter, filtering out all very low frequencies. So we have these, it's barely present here, but a different image. You have a very, very sharp front. I do not have an image of this, but this bright front stays, and it propagates through here. This is a very unique form of wave, which we call atmospheric bores. We have another one here. This is very interesting because it's curved. However, half an hour earlier when it was down here, it was straight, and suddenly it started to bend. Part of it stopped to move, but the other one kept progressing. So it tells a lot about the environment, but it also raises a lot of questions. So what is going on there? If you don't have any coincident measurement of temperature or winds and so forth, it's really difficult to tell what's going on. So we're trying to model this behavior and see what could produce this kind of dynamics. The imager can also measure aurora. This is what we call a proton aurora. So this is actually the near infrared, very, very bright. It stayed there like a soup for a long, long time. This here is a typical aurora image we get any nice, but you see these little holes up here. These are like tubes extending up vertically in the atmosphere. The instabilities, what we call Kelvin-Helmholtz instabilities. This one is dynamically, it's not really interesting in it, but this one was actually taken on Valentine's Day 2011. Which I found very amusing. When I saw it, I was like, oh, it can't be. So I double checked the date. That's right, it was taken on Valentine's Day. This picture is taken down from Council Reef. Again, this is a horizon of fish islands. Council Reef National Park has some of the absolute darkest skies in the US. Not just in the US, in fact, on the entire North American continent. The darkest skies you find in that region is in southern Utah. So there's no better place to actually put these instruments. So we got a trailer that we're putting down there. We're still waiting for the license plates when they get there. I tail it down, they put some instruments in it. This is a recent instrument we got. This is an infrared imager, which means it doesn't care about the aurora. It's going to be shipped to Alaska next weekend. We're just testing it right now, playing around with it. And this is the camera sitting up in Alaska. When it's down here at Capitol Reef, it's sitting in the box we have right here, just looking straight over the skyline there. So here are some examples for Capitol Reef. These are not processed data, so we're not trying to extract the wave out so it stands out. But you can see some wave structure in here. These are the cliffs surrounding the field station. How many of you guys been down to the field station? Just a few of you? So the field station is surrounded by these cliffs, so you can see that here. This is another example. This is the infrared. You can now see how much brighter this is. This is not clouds. This is actual air flow. But we're looking at that. Remember that orange part of the spectrum? We're getting much more of that light instead, so it's much, much brighter. It's like a big suit. There should be a movie that will play. And this is actually taken from my backyard last night. Testing the camera, we just got it calibrated last night. Again, this is not processed, this is raw data. You see some waves coming, moving in all kinds of directions. When we process the data, they will stand out. We can analyze the data from where they're coming from and so forth. The nice thing about it is taking the backyard, it doesn't really care about the ambient light. So we could in principle take this camera here, we could put it right downtown Provo, right near a light intersection, and you will get the same data. It wouldn't look any different. The reason you start seeing light over here is because the lens actually froze up. The computer was also outside, and that froze too. It literally froze. Battery completely died on it. Here's some students that work with me presenting at something called CEDA. It's an international conference. They held in Boulder last year, where I presented some of their work. We're really excited about this. We just got a GEL grant to establish a high altitude research program. So the idea is to take a microcontroller, like a small computer, something called Raspberry Pi. We'll put in small boxes. Actually, we'll build little cubes, put them in there, make some payloads. We can look at cosmic rays. We can look at ozone, whatever we want to look at. Launch it with balloons. And the idea, the goal is to gain some experience. So maybe a year or two from now, we can put them on rockets. And a few years down the road, we can actually put them in these little boxes and put them on a satellite. Actually, not put them on a satellite. This is a satellite. It's called a CubeSat. But NSF is very eager to support undergraduate research involved in CubeSats. So here's the final slide. And let's play this one, and then I'll take any questions. But this is airglow and aurora from space. So, any questions?
I have a question about that 22-year cycle on the magnetic reversal of the sun. Is that 22-year cycle in coincidence with the 11-year cycle? Is part of it?
It is. If you look at the sunspot activity, it starts at the poles of the sun and then migrates towards the equator. And when it comes back, the polarity is reversed. So it is coincident with it's an envelope of the 22, it's an envelope on the 11-year-old cycle.
Do you get enhanced weather effects because of the when it does that reversal?
I haven't seen it myself, but I heard people saying you can see it in climate data.
An enhanced 11-year cycle or something?
The 11-year cycle stand out in climate data. I have not seen myself. I have not seen it for myself. The 20-year-old cycle. I've been told it is present in climate data, but certainly not as strong as the 11-year cycle.
Hey, we better wrap it up to give the next talk time set up. Thank you.